Hello everyone, back with the thermal physics lecture video 2 for the class that we will not have in person on this coming Tuesday. Let's get started. This is where I stopped the previous video, the equipartition theorem. Think about this. We have used this quite a lot. However, we have never had a formal proof, right? We have invoked it quite a few times. This is the opportunity for us now to actually prove this using the Boltzmann factors. That's the beauty of it, right? First of all, let me a rather brief recap. What is equipartition theorem? If you all remember, at temperature T, the average energy of any quadratic degree of freedom. I'm writing this out explicitly so that you will know now. DOF, I have used this a lot, is half kBT. This is what the equipartition theorem states. If you remember, we took this a little bit further and we said for a system containing n molecules, each with small f degree of freedom, the total thermal energy can be given as U of thermal is equal to NF half kBT. This is something we know about the equipartition theorem, and this is what we know from the past, right? In this thing, don't forget you're talking strictly about the quadratic degree of freedom, right? So in fact, we should just make sure we are not including any non-quadratic terms. So no non-quadratic temperature dependent forms of energy. Right? So obviously we know this. Equipartition theorem doesn't apply to all the systems. It can only apply to systems whose store or whose energy is in the form of quadratic degrees of freedom. What is this form? Energy, let's put this down explicitly now. Energy is in quadratic DOF. In this case, let's define that as E of Q is equal to CQ square. Quadratic term, right? And here, C is a constant, obviously. C is a constant coefficient. And think of Q as any coordinate or momentum variable variables such as x or px, let's say momentum, or even angular momentum, right? Any of this could actually be given here by Q, right? In a system like this, think about this. In this case, let's start with the simplest. We always do that, right? Let's consider a system with 1 degree of freedom. Let's consider a simple system with 1 DOF, and it is in equilibrium. You know the acronym equilibrium with a reservoir at temperature T. We need to make this setup, right? This is how we are going to use the Boltzmann factors here. This is what we started out in this chapter, right? So we need to make sure that this system we are looking at, a simple system, 1 degree of freedom, equilibrium with a reservoir at room temperature. In this case, what we are going to do is assume that all the energy levels, let me draw this diagram, a rather brief diagram here, right? All the energy levels are quantized, discrete, with a very small spacing of, let's say, delta Q, something like this, right? Over here, think of this as Q, and any of this thing is delta Q. Assume over here that all levels are quantized. You all know what it means. Assume that energy levels are quantized. At this point, what we are going to do? Well, and again, quantize and with, let's say, a small spacing. This is what I drew here, delta Q, right? With small spacing, very small spacing, delta Q. In this case, what we are going to do, let's write down a partition function for this system. Eventually, we are going to somehow try to calculate the average energy of the system also. And let's see where we end up with, right? Let's use our fundamental idea of now writing a partition function for a system like this, single degree of freedom, and in contact or equilibrium with the reservoir, right? If I start writing this partition function down, then you have Z is equal to, obviously we got to sum over all the states, Q. If you remember that previous diagram I drew, all states, e raised to minus beta E of Q. Beta, you all know, is 1 over kBT. From here on, we generally use that. It's easier, right? Solve this further. Substitute the value for E of Q is equal to summation E BCQ square. Right? In this case, actually, to count the states, what we can do is because they're discretely spaced, separated by delta Q. As long as it is very small, I can actually multiply inside and outside the sum by delta Q. I can easily do that, right? This is an easier way to somehow evaluate the sum. So I'm going to do that. It's a very small value, just so that it's extremely small. As long as delta Q is small, we are fine doing that. And I can, at that point, 1 divided by delta Q, summation of Q, e raised to minus BCQ square times delta Q. Now what can we do? Think about this. Now this summation, we have done this in the past, can be interpreted by area under a bar graph, right? That can make our life easy. Now this sum, let's put this down. Sum can be interpreted as area under a bar graph whose height is going to be determined by Boltzmann factor. T is missing, Boltzmann factor. If I draw this figure rather briefly or rather quickly here, let me take a look here. What are you looking at? Looking at a graph like this. Over here, this scale is Q, obviously. Height is determined by the Boltzmann factor. That's what we claim. And in this case, the height is determined by what? This is going to be e raised to minus beta CQ square, right? And what is this bar graph? I can draw something like something like this qualitatively. You all know not to rely too much on the diagrams I have drawn here, even though this should have been centered, to be honest. So this should be, take a look at this. This should be more of a centered curve here, right? And delta Q here is very small. And as a result, we can approximate this by a smooth curve. It's always right? The partition function here is literally, I can draw this, let's draw this with a, something like that. Partition function is the area now under this bar graph whose height is the Boltzmann factor. To calculate this area, what we can do, we can pretend that the bar graph is smooth enough. If you pretend and if you make that assumption here, then we can convert this into an integral. Then it makes our life really easy. Solving that integral should not be too tough. This function, you might all know, looks more like a Gaussian, but more about that in a minute, right? So let's solve this now. Therefore, I can now say z is going to be approximately equal to 1 over delta q. I'm talking about this term, minus infinity to infinity, all the states in this case, and integrating minus beta c q square dq. Solving this integral, I would say it's a one-step process as long as you make a good, clear, assumption here. So let's put this down and let's simplify this. Let x is equal to under root beta times c q. As a result, if I do this, then I have dx is equal to beta c times dq, right? That means one way to say this is x is equal to, this is fine. This should work. Once we have that, now let's substitute. Let's substitute over here. So let's put down the partition function now. Z is equal to 1 over, approximately equal to delta q, 1 over under root bc, beta c times integral minus infinity to plus infinity e raised to minus x square dx. Take a look. All I have done is made the change accordingly here, and in place of dq, I have somehow gotten now here dx, right? And that, as a result, the denominator also has 1 over under root beta c. We are not going to solve. So here's the thing. In this semester, I have ran out of time in certain cases. In the past, I generally used to go through one of these long integrals in the class. I'm going to still keep that in the notes eventually. So you all can, if someone wants to solve those integrals in principle for physicists, you all should be perfectly fine to do that, right? Right now, what we do is we take this value. This is a value we can actually do away with. This is given by under root pi, appendix B. Take a look, anyone interested, take a look at appendix B, and we are going to get this value directly from that. Why? Because the function e raised to minus x square, actually, if you all know this form, the familiar form, is called a Gaussian, right? It's all, as I said earlier here, it's called a Gaussian, and unfortunately, its antiderivative cannot be written in simple functions that we know. We can directly choose this from the appendix, and we are perfectly fine. At this point, I would say let's move on. You will see at least in the class one more integral like this, which I will try to solve, okay, at least in the notes. Once we do that, let's solve it further. Therefore, partition function now can be given as 1 over delta q, the root pi over beta c, because I took the value for pi from that, right? Therefore, solving further, z is equal to c beta raised to minus 1/2. I'm going to just block this and say that over here, I have included all of this. C, a capital C, is equal to pi over c divided by delta q. Just an abbreviation, small, set so that it makes easier, because we're going to keep in mind, we want to somehow differentiate this also. I would like to differentiate this z with respect to b. I hope you all know where I'm going with that, right? We want now to calculate the average energy. So using this to calculate average energy of this system. Therefore, E is going to be equal to minus, I'm using just one of those relationships which gives us that, right? Derivative of Z with respect to beta, as I said, as long as I have something in the beta form, that's the most important part, because the derivative is going to be taken with respect to that. Nothing else actually is going to matter much here, right? Substituting everything, this is now minus 1 over C beta time raised to minus 1/2. This is, I'm plugging this value for Z from here, times partial derivative with respect to beta for C beta raised to minus 1/2. Take a derivative. You all are good with this. Is single step derivatives. This should be minus 1 over C beta raised to minus 1/2. For this derivative, the minus 1/2 is going to obviously come in front, and then C beta raised to minus 3/2, right? Minus 1/2, minus 1, minus 3/2. That's the derivative you're going to take. Take a step here. Simple algebra. Just solve for this, and the answer you end up getting is 1/2 beta inverse. Or if I plug the value now of KBT, this is going to be equal to half KBT. Remember, this was actually, and if I go here and state this was the equipartition theorem for 1 DOF, 1 degree of freedom. If someone told you to calculate the heat capacity over here, you can go ahead and do that also. It's going to be KB over 2. Interesting, right? We started from something rather simple. So far, we have not proved this, equipartition theorem. This was a good opportunity for us. Note that all the constants vanished, right? They all canceled out. It's fascinating. It's a very simple way to prove this theorem. Another important fact that you all should note here, that the proof that it does not carry over to quantum mechanical systems, right? If the number of distinct states has let's say very small probabilities, then the smooth Gaussian curve that you have used for a good approximation, it will not work out. It will not work out that way. We try to discretize energy. We try to use a more of an, and you at this point you all will have anyway noted that, think about the Einstein solid case in the past, right? We saw that in that case. The equipartition is true. Equipartition theorem is only holds in the high temperature regime, where many states are contributing, and therefore the spacing of the states is not important. So don't forget that. I would like to make a note here. This is fundamental and important. The approximation of converting summation to integral works provided the spacing between the energy levels delta E is very less than KBT. Think about this. Approximately KBT 1 over 40 EV for room temperature, right? So anytime, in this case, degrees of freedom or DOFs with energy level spacing much larger than this are anyway frozen. Interesting, something we have used all the semester, throughout the semester. Actually, we have proved this theorem more into the, in the regime of thinking about this classically. I would urge you all to think about this as a classical problem where we have not always, again, it does not apply to all systems. We have known that in the past. We took an example, for Einstein solid, And the entire proof we went through, we have literally analyzed the system in classical mechanics, right? Where each value of the Q is going to correspond to a separate but independent state. That's all we have done. Trying to do one problem based on this from the book, and then I'd like to go to Maxwell-Boltzmann distribution, right? So let's do that. Let me do one problem on this topic. The problem I'm looking at here is problem number from the book 6.31. Right? What the problem is saying is pretty similar to what we did in the class. I'm just trying to reinforce this whole derivation. Right? The problem states that consider a classical degree of freedom. Right? A classical DOF that is linear rather than quadratic. Linear rather than quadratic, right? E is equal to CQ. That's what it's given us. For some constant C. C is a constant here. C is constant. An example will be like the kinetic energy of a highly relativistic particle in one dimension, written in terms of its momentum. That's what the problem is stating. What it's saying is repeat the derivation of the equipartition theorem for this system and show that the average kinetic energy is E equal to, what it's telling us is shows that E is equal to kBT for a system like this also. Let's start. It's almost like reinforcing what we did earlier, and that's the only reason I'm interested in it, right? So state Q over here has energy CQ. So the Boltzmann factor, let's write down the Boltzmann factor. That's our first step. So the Boltzmann factor for this state is e raised to minus beta C Q. By this time, I'm assuming you all are now familiar how to quickly put things in terms of Boltzmann factor, right? You're always going to do that exponential relationship, e raised to minus k, whatever that energy es over kBt, because I'm doing 1 over kBt is beta, that's what I have here, right? And from here, I can now literally sum over all the Boltzmann factors, and that's my partition function. That's one easy way to follow such problems. It makes life very easy. If you all understand how to write down the Boltzmann factor, and then from there on, just take the sum, you're good. As a result, partition function z can be now written as summation of all the states q, e raised to minus beta C Q. I hope you all agree with this. We're going to take this now. If we take the idea that the delta Q is very small, as we did for the equipartition theorem, then I can actually multiply and divide, follow the same recipe we did in class for equipartition theorem. Let's put that down. That is, Z can also be written as 1 over delta Q, summation of Q, e raised to minus beta C Q, and multiply here by delta Q. Anytime over here, the sum can become an integral. We did that, right? We also claimed that the transformation from sum to an integral will work depending on what we have chosen as the energy, right? In this case, in the limit, the delta Q goes to 0, very, very small, sum becomes integral. We did that. So let's put this down now as an integral. Therefore, I can write down the partition function for this system is 1 over delta Q will stay here. This delta Q is going to become dq. I'm going to sum over all the states from negative infinity to positive, e raised to minus beta C Q dq. Note that this integral is going to be symmetric now. This integral I'm talking about, symmetric under Q to minus Q. You all know how I can change these limits, right? From minus infinity to infinity, I can actually go from 0 to infinity here, right? I can do that. We can write this as a little bit of mathematics, and I am assuming you all have done this, something like this. We can write it as twice the integral or only the positive value, half of it, right? Only the positive q values. Do that. Let's do that then. Therefore, z is equal to 2 times 1 over delta q integral 0 to infinity e raised to minus bcq dq. Solve this integral and let's put the limits. Okay, let's try to solve this integral, put the limits and see where we end up with. If I continue, that's going to be equal to 2 over delta q minus 1 over beta c e raised to minus bcq and the limits 0 to infinity. Right? All I have done is taken that integral for e raised to minus bcq, and that's what I get, 1 minus 1 over bc, and this term survives. All the values for infinity is going to go out. 0 is going to be converted to 1. And what am I going to get? This is going to be equal to 2 over, I have skipped a step here, but feel free to solve this out explicitly if you want, bc delta q, right? Why? Because everything else is going to go away over here. Only the term with the 0 is going to matter. This is going to become 1, right? And minus is going to take care of the minus sign. So it's going to become positive. And if I solve this further, this is c beta inverse. And over here, I can somehow say this capital C, that constant, is 2 over that small c delta q. We did something like this for the equipartition theorem also, so that we only have the dependence on beta, right? Because you all know now that I am looking for average energy. If we are looking for average energy, that means we definitely want that, right? Beta. Therefore, the average energy is now written as symbol. The first formula, I'm going to use the first relationship. And differentiating with the partition function with respect to beta. And in this case, I have minus beta over c, partial derivative with respect to beta for c beta inverse. This is minus 1, this power is going to become minus 2, that is going to be minus sign in front. Let's solve that. Minus beta divided by c. As I said earlier, this minus sign comes in front, beta raised to minus 2. Therefore, over here, the average energy is going to be 1 over beta. If I solve this further, I end up with 1 over beta. This is nothing but kBT. This is what the problem actually did ask us. It's almost like verifying if you understood the equipartition theorem proof, and it will really help you. Okay. What I'll do is I'll stop this lecture right here. And the third lecture for this class that we have missed is going to be on Boltzmann distribution. A really, really fascinating concept as well. Let me stop here and make a third video, and I'll post all of these 3 online and I'll provide the instructions. Okay. Thank you.